Hey guys, chapter 4 in your textbook, basic probability. A couple of things going on in this video. First of all, I'm going to go through a PowerPoint. It is available on Blackboard under the week that you are, of the assignments, the instructional videos that you're currently working in. And then at the end of this video, I'll get out a PowerPoint and I'll start working some problems. Now, under the, if you go to Blackboard under Content, one of the folders you'll see is handouts. And I think it's either the third or fourth handout, but anyway, it'll be called Counting Problems Practice. So again, two things. The PowerPoint, and you may want to go ahead and, which again, the PowerPoint is available to you. You might just want to kick your shoes off and prop up your feet and sit back and watch and take notes, of course. But I do think you'd want to go ahead and print out the handout that's available on Blackboard. So, guys, let's do it. Let's get this done. Objectives for this video is to try to teach you just very basic probability concepts, and then we're going to get into something called counting. One thing to remember when you're talking about probability deals with randomness. And, a lot of people, a lot of times people know I'm a statistics professor, and they'll want to either challenge me or amuse me or entertain me by asking me probability questions. And I was at Keeneland. I don't know if you've ever been to Keeneland, but it's a place where they race horses. If you've never been, you should go. It's in Lexington. It's absolutely gorgeous. They have spring meet and fall meet, and it's really, really pretty. Even if you don't like horses, you would like Keeneland. So there you go. There's free advertising for Keeneland, right? But people will ask me, they'll say, well, what's the probability horse number 5 wins? Well, probability doesn't even apply unless we're going to choose the horse randomly. So if there are 7 horses that are running, and we're going to put all their names in a hat and pull out a horse at random, and that horse just happens to be the winner, then the probability is 1/7 that horse wins. But guys, we don't race horses based on randomness. It's kind of like if 2 guys walk into a room and let's say there's a dating show and a girl gets to choose one of the 2 guys, and one of the guys is really good looking and has an excellent personality, and the other guy has a horrible personality and doesn't look so good. There may be only 2 guys there. You might say, well, the probability she chooses one guy's 50-50 or 0.5, but it's not unless she's choosing the winner randomly. So, guys, very, very, very important. When we talk about probability, we're talking about a random event, that the selection is at random and not by some other choice. I see this in like basketball, and I'm a huge Kentucky basketball fan. Well, what's the probability that Kentucky wins the SEC this year? Well, probability doesn't apply unless we're implementing new rules for winning the SEC where we choose the winning team randomly. And I certainly don't want that, because I think there are now 14 teams in the SEC. Trust me, Kentucky has a better than 1/14th probability, even though probability doesn't apply, of winning the SEC. So insert a little snide remark from a very confident Kentucky fan. All right, guys, get back to the real stuff here. Basic probability concepts. First thing you got to remember is probability will always be a number between 0 and 1. And again, it deals with randomness. So if somebody tells you the probability of attaining some particular event is 1.2, then that's impossible. The probability has to be between 0 and 1 inclusively. Guys, the probability of 0 tells you it's never going to happen. Probability of 1 tells you it's going to happen each and every time. Assessing probability, there are 2 approaches. Priori, based on prior knowledge. I'll give you an example in just a second. The probability is easy to calculate. You just take the number of ways that something can happen over the total number of outcomes. Empirical probability is the same way. The number of ways the event can occur over the total number of outcomes. They just set up a little bit differently, even though the calculations are the same. An example of priori probability, when randomly selecting a day from the year 2015, what is the probability? The day is in January. Well, guys, in 2015 it wasn't leap year, so there were 365 days. There were 31 days in January, so the probability would be very easy to calculate. And it's priority because it happened in 2015, which is prior to today. Empirical probability is where we kind of collect our own data, and in this case they've tabulated and organized it in a contingency table. But so we look at the numbers that we collected. Empirical means experimental in a sense, so we actually have collected this data, and we've divided into people taking statistics and not taking statistics across gender. So the question, what's the probability of a male taking statistics? Well, we can see that the upper left-hand cell, where male and taking statistics, has 84. So there's 439 total students, so only 84 of them are male and taking statistics, so the probability would be easily calculated at 84 over 439. Now, something I like about this screen that I don't like about the screen before is it shows you at the bottom right that the probability can be either a fraction or it can be a decimal. So the correct answer here would be 84 over 439, or 0.191. Events. What do we mean by an event? An event is something that's described by a single characteristic. Example, a day in January from all days in 2015, or choosing an ace from a deck of cards. Events can be very simple. Events can be very complex. Probability, as a statistics professor, one of the hurdles I have to get over in preparing for this class is how much time I'm going to spend on probability. Because I tell you, probability is really cool. As someone who goes to Las Vegas, or well, used to go to Las Vegas, especially before kids, probability is super cool. In fact, Las Vegas is built on probability. Every game they offer out there, the probability of you winning is less than the probability of the house winning. So that just tells you over a long sequence of trials that day in, day out, the casino is going to win. But in the short term, who knows what's going to happen? So that's why we go to Las Vegas, because we play these games in the short term. So a simple event may be you're playing a roulette wheel, and the simple event is the ball going in a black slot. Sample space is a collection of all possible outcomes. If we're rolling a die, you have 6 sides. If we have a standard deck of cards, which they call a bridge deck, you have 52 cards: aces, kings, queens, diamonds, spades, and all that stuff. Simple probability refers to the probability of a simple event. And guys, again, don't forget, it's random. So the probability here, now notice the notation they've used at the first red bullet. The P parentheses January means what is the probability of being in January. Well, you can see at the very bottom that if we look at the column under January, we have 4 in Wednesday and 27 not Wednesday, 31 total. So the probability of being in January would be the 31 out of the 365. Now, putting a little different spin on it, what's the probability the day was Wednesday? Well, if we follow the first row, well, actually it'd be the second row over of Wednesdays, we can see that we had 52 total Wednesdays in 2015. So 52 out of the 365 days would give you the probability. So 52 out of 365. Sorry guys, I got a, well, doesn't matter. Okay, joint probability refers to the probability of an occurrence of two or more events. Now, in this situation, we're just looking at two events. So if we look at the first red bullet, probability of it being January and Wednesday. So you can see that where the row and the column meets for Wednesday and January, there were 4 that were counted. So then we would have 4 out of 365. Probability of January and Wednesday. Probability of not January would be, and not Wednesday, then we'd have to count up all the other squares. So not January and not Wednesday, you can, well, not count up the other squares. You just follow the row and follow the column of not Wednesday and not January. So you see that you have 286 in that particular cell. So when you've got a contingency table like this, finding joint probability is very easy as long as you set your table up in the way that the questions are phrased. For example, if I wanted the probability of a Tuesday, well, I can't get that from this table because I have Wednesday or not Wednesday. Now, granted, Tuesday is not Wednesday, but so is Thursday, Friday, and so on. Mutually exclusive events means they cannot occur simultaneously. So if you want to know a joint, like the previous problem, a joint probability that a day is in January and in February, you can't do that because a day can't be in the 2 months. So we would say that these events are mutually exclusive. Marginal probability example. Guys, I tell you what, for now let's skip over that. I meant to delete that slide. And what I wanted to do next was just summarize what we've done so far. So, guys, probability is a numerical measure of the likelihood that a random event will occur. Guys, probability has to be between 0 and 1. Probability of 0.5 means it's equally likely. 1 means it's certain to happen. 0 means it's not going to happen. Now, we get into something called counting, and I think counting is some of the cooler stuff that we do in probability. We probably all have played the lottery sometime along the way, and you can actually use rules of counting to calculate when it's advantageous, or at least probabilistically advantageous, to play the lottery. I think the way the numbers are set up on the Powerball, I think if the Powerball gets to about 235 million, then it becomes in your best interest in terms of probability. But all that said, the probability of you winning is so small, and you get into something called expected values, and we may talk about that in a later video. But guys, counting rules are very useful in computing probabilities, especially when there are a large number of possible outcomes. Counting rules can be used in these cases to calculate, compute probabilities. Because you can imagine, again, the way, going back to lottery, I think there are maybe, I don't even know, maybe 56 numbers, and then there's the Powerball. You can imagine trying to go through and model all of the possible outcomes. It would take forever. Well, I don't know about forever, but it would take a long time. So these counting rules help you model those types of events. Now, the first counting rule, there are going to be 5 of these. The first counting rule is the simplest. And it says if any one of k different mutually exclusive and collectively exhaustive events, guys, that's just a bunch of big old fancy words to say that the conditions apply, can occur on each of n trials, then the number of possible outcomes is equal to k raised to the nth power. Now, so if you roll a fair die 3 times, then there are 6 raised to the third, 216 possible outcomes. The reason they're mutually exclusive, and we can say that they're independent. So we roll the die, and then we roll it again. What happened on the first row, I should say what happens on the second row is independent of what happened on the first row. Counting rule number 2, if there are K1 events on the first trial, K2 events on the second trial, and Kn events on the nth trial, then the number of possible outcomes is the product of K1, K2 up to Kn. This is much better seen through an example. So if you want to go to a park, eat at a restaurant, and see a movie, there are 3 parks, 4 restaurants, and 6 movie choices. How many different possibilities or combinations are there? Well, you can get that by just multiplying 3 times 4 times 6 to give you 72 different possibilities. So we wonder, my wife and I wonder why we never can make a decision. Well, there you go. There are how many movies and how many restaurants in Lexington and how many different, so that's why it's so hard. Counting rule number 3, the number of ways that n items can be arranged in order is just n factorial. So when you see n with the exclamation mark, it's not that the n is excited. It's a mathematical operation that tells you to start at n and multiply that times 1 minus the number, times 2 minus the number, times 3, all the way down to 1. So at the bottom you can see that, well, the example, you have 5 books to put on a bookshelf. How many different ways can these books be placed on the shelf? Well, if you think about the first place, there are 5 ways that you could put books into that one place. You could choose the first book, the second book, the third book, the fourth book, or the fifth book. Once you decided which book goes into the first place on the bookshelf, you only have 4 ways to fill the second. Because you've already used one of the books, you only got 4 books left. After you choose that one, you've already identified where 2 of the books are. You have 3 books to go in the third slot, and so on and so forth. So the answer is 5 factorial, which is just 5 times 4 times 3 times 2 times 1. Counting rule number 4, permutations. Permutations when order matters. Now we're going to get into something called permutations of combinations. The thing you've got to tattoo to your brain is when order does not matter, we look at a combination. When order does matter, we look at a permutation. So a permutation, the number of ways of arranging X objects selected from N objects in order. And the notation is N, capital PX. And we find that by taking n factorial divided by n minus x factorial. So, example that, you have 5 books and are going to put 3 on a bookshelf. How many different ways can the book be ordered? Now what that's telling you is that if you put book number 3 on the first place, book number 5 on the second, and book number 1 on the third, so 3, 5, 1, that's a different ordering than 5, 3, 1. Even though you got the same books, the third book, the fifth book, and the first book, the way they're ordered matters in the problem. So when order matters, you've got a permutation. Now if order didn't matter, you have a combination. Speaking of, the number of ways of selecting X objects from N objects, irrespective of order, is the notation is n capital CX, and it's n factorial divided by x factorial times n minus x factorial. Guys, we got a fancy key on Stack Crunch that does these calculations for us, and I'll show you how to use those in the example problem. So example here, if we have 5 books, we're going to select 3 that we are to read, ignoring the order, so we don't care whether we read the 5th book first and the 3rd one second and the 1st one third, or whether it's 3, 5, 1 or 1, 5, 3. Order does not matter. When order doesn't matter, we use a combination. So we would use the formula to get 10 different possibilities. Now I'm going to put up a video on simulations using, I'll put it up probably this week or next, looking at the way that we can model phenomena using simulations. And look at the likelihood of things happening. So guys, anyway, that's the end of this. Let me get out of the PowerPoint, and I want to go to the presenter. And I've got some counting problem practice that we want to look at. Okay, well, I don't know if we want to look at it, but I want to look at it. And let me make sure that this is as clear as it can be. So, number one, if there are 10 multiple choice questions on an exam, each having 3 possible answers, how many different sequences of answers are there? So I like to look at this as slots. So imagine these being question 1, question 2, all the way down to question 10. Well, if we think about it, if each has 3 possible answers, there are 3 ways to get an answer there. There are 3 ways to get an answer there. In fact, there are 3 ways to get each of these, so it should make sense to you that the number of possibilities would be 3 to the 10th power. So that's an example of the counting principle number 1. Number 2, if a coin is tossed 7 times, how many different outcomes are there? Well, again, just like this one, we have 7 times that we are, so we have 2 outcomes there, head or tail, 2 outcomes there, head or tails. So it should be easy to see that the outcome, the total number of outcomes would be 2 to the 7th. If a die is tossed 7 times, how many different outcomes are there? Well, this is kind of modeled the same way. We have the die 7 times, but instead of 2 possible outcomes, we have 6. 1, 2, 3, 4, 5, or 6. 6 there, 6 through all of those. So it should be pretty obvious that we have 6 to the 7th possibilities. Number 4, you would like to build your own burger at a fast food restaurant. There are 5 different breads, 7 different cheeses, 4 different cold toppings, and 5 different sauces on the menu. So not only is it hard to determine where you're going to go when you've got all these different choices, it's hard to even decide what you're going to order once you get there. It kind of reminds me of, I don't know if you guys have been to Cheesecake Factory, if you've been there lately, but their menu is like an encyclopedia. You know, it's just insane. So anyway, there are 5 different breads. There are 7 different cheeses. There are 4 different toppings. And there are 5 different sauces. So the probability here would be 5 times 7 times 4 times 5. I don't know what that is, but you can do it. All right, in Major League Baseball, there are 5 teams in the Eastern Division of the National League: Atlanta, Florida, the Mets, Phillies, and Washington. How many different orders of finish are there for the 5 teams? Well, the first place team, you know, again, if we're doing this randomly, there are 5 ways to fill it. The second place team, since the first place team has already been established, there will be 4 ways to fill the second. There will be 3 ways to fill third place, 2 ways to fill fourth place, and then whoever's left over has to fill the last. So guys, the different orders of finish for these 5 teams would be 5 factorial. Are these orders equally likely? Well, no. Because if we assigned the winners, and it'd be kind of boring if we did this, but if we assigned the winners of the Eastern Division National League randomly and pulled the winner out of a hat, again, blindfold randomly, then yeah. But guys, we know that the way that we assign first place isn't by random assignment. Hopefully it's the best team. It's definitely the team with the best record. Alrighty, moving right along. This shouldn't take long, actually. A gardener has 6 rows available in his vegetable garden to place tomatoes, eggplant, peppers, cucumbers, beans, and lettuce. Each vegetable will be allowed 1 row. How many ways are there to position these vegetables in the garden? Well, whatever goes in row 1, there would be 6 ways to choose it. Once it's selected, we move on to row 2. There will be 5 ways. 4 ways for row 3. I think we can generalize here that there would be 6 factorial ways to position these vegetables. All right, number 7. 4 members of a group of 10 people are to be selected to a team. How many ways are there to select these 4 members? Now, guys, when I read this problem, I think, well, it's going to be either permutation or a combination problem because you have a larger group and you're looking at the way to arrange a subset from that group. Now, the next thing I look at is order important? Well, it either is or it isn't. Guys, if order does matter, we need a permutation. If order does not matter, we have a combination. Now, let's think about this problem. How many ways are there to select 4 members? So, let me ask you this. If I have 4 members of Bob, Tom, George, and Sally, is that the same committee as Sally, George, Bob, and Tom? Well, obviously, order doesn't matter for the committee to be the same. So order does not matter. So guys, this one we are in a combination. So what we're going to have is we're going to have a combination of 10. Choose 4. Now, let's see how we figure that out using Stack Crunch. So let me get out of here and go to Stack Crunch. Now, okay, shoot, guys, I forgot how to do this. Okay, let's go to Data. Let's go to Compute, and let's do an expression. Now, what I want to do here is I have a combination, so I'm going to do COMB, and guys, I don't remember whether that's capitalized or not. I'll tell you what, let's just go build. So we can come down to, so it's lowercase, so I'm going to choose that. Now, the first thing I put is the bigger number, and then I put the smaller number, and I need to actually delete that. So I have COM for combination, 10, 4, because I have 10 people that I'm selecting a committee of 4 from. Select OK, hit Compute, and my answer is 210. All right. Number 8. A daily lottery is conducted in which 2 winning numbers are selected out of 10 numbers. How many different combinations, so guys, this kind of tells you what you need to use, of winning numbers are possible? Well, guys, this is pretty simple. We have 100 possibilities, and we're choosing 2 of those. So guys, go back to to this. So data, compute, expressions, and I need to change that to 100 and this to A2. So the answer would be 4950. All right, guys, only 2 left. I don't know about y'all. I kind of find these fun. Maybe that just says I have an insane brain, but I kind of do. Number 9, how many ways could we get first, second, and third place winners in a division with 6 teams? Now, does order matter? Well, I mean, obviously it does. Because first, second, third is different than, well, arrangement matters, so order does matter. So what we're going to do here is we have 6 total. So we're going to do a permutation, 6, choose 3. All right, 6 teams? Yeah. So let me show you how to do that. I don't like those boxes open. So I want to go to data, compute, and now I am going to use perm. So I have 6, 3. So I enter just like that, hit compute, and so there's 120 possible outcomes. Finally, number 10, how many different 4-letter passwords can be created for software access if no letter can be used more than once? So we have a 4-letter, so the first letter, second letter, third letter, fourth letter. All right. Does order matter? Well, obviously, if we have a passcode of ABCD, and we try to put in DCBA, well, it's not going to let us. It's got to be in the order. So order does matter. So we're going to have a permutation here. And we have, let's see, how many, so we're talking about letters. So there's 26 of those. And we are looking at 4. Now, I showed you how to do this on Stack Crunch. I want to show you on a calculator. If any of you have like an 83 or 84, they're much more common these days because so many high school classes require. You know, if you don't worry about it. But you know, it's something that may keep you from. If you have one of these, it'll keep you from logging on to Stack Crunch if you don't want. It's a little harder. So what we do here again, we're trying to solve this permutation. 26 objects, 4 taken from the 26. So what I would do is I would type in the 26, then I'm going to go to the math key. I'm going to go over to the right. Let me make this a little clearer. I'm going to go over to the right where it says PRB, which stands for probability. We are looking at a permutation, so NPR. And then I choose 4. So the answer would be, I knew it would be like 358,800. Now, just to make sure that this calculator did something wacky, let's make sure that we get 120. And of course we are. I'm not going to show you how to do something. So we had 6. Choose, what was it, 4? No, 3. And you'll see we do get 120. So guys, whether you do it with your calculator, most scientific calculators have permutation and combination operations on them. So, but Stack Crunch can do it as well. Guys, I'm done. I hope you enjoyed this video. I actually kind of had a little bit of fun working these things. Something that I always find kind of interesting is is today, with passwords. This is actually from a previous video, as you can tell. But you think about passwords today, and let's say we're restricted to maybe 8. And we're allowed to use lowercase letters and numbers. So if you think about it, lowercase letters and numbers, there would be, if using 0 through 9, there would be 36 ways to fill this, 36 ways to fill this, 36 ways to fill this. Now, if we don't have, if we can't reuse numbers and letters, then there would be 36 here and then 35 there. But if like M7, if you can reuse the numbers, then there would be 36 ways to fill this, 36 ways to fill this, and 36, and so on and so forth. But think of the effect of the number of outcomes if you allow capital letters, so you distinguish between lowercase and uppercase. Well, this 36 becomes 36 plus 26 more, so you have 62 possibilities in each one of these. And you can look at your calculator, the number of outcomes increases drastically. Then throw in special characters. All those. So it's pretty clear that it's impossible, well, not impossible, but very, very unlikely to guess a passcode of 7 digits using capital letters, lowercase letters, numbers, and characters. But we all know that there are other sneakier ways to figure those things out. So, guys, I'm done. Have a great one.